Notice now her ears are perked right up. Comes to making wine, she'll get 100% on this one. So we're going to go ahead and we're going to add the yeast, and we're going to let this ferment for 3 to 5 days for red wine, and we're going to let the juice come in contact with the skins, and 7 to 14 days for white wine. Don't ask me why. I used to know, I don't anymore. And by the way, if you let the white wine stay in contact with the skins of those grapes, the wine is still going to stay a yellow color, agreed? Okay. So that's the fermentation lengths for each of these. Next is the aging. The important concept is the following. It would be nice if we could take wine, whether it's red wine or white wine, and we could put it into a barrel made out of oak. Because then the wine is going to extract the flavors of the oak wood into the wine itself. And there's several ways we could do this. We could do it with American oak barrels, which are not as expensive as French oak barrels. So first you get to pick the barrel, American or French oak. French oak is more expensive. So you could use French oak barrels, and then you could do another thing. You could either use the barrels once and then throw them away, or you could use them to make several batches. So what if we used French oak barrels, and what if we used the barrels one time and threw them away, and then bought another set of barrels and poured the wine in there and let it sit for a long time and then throw them away after we get the juice out? Would that explain why some of the wines cost a lot of money? Mm-hmm. Let's think about the cheapest way we could do it. Some of the companies will take stainless steel tanks like this, and they'll take 2x4s that are made of oak and put 2x4 lumber into the tank and put the lid on. That's the cheap way to do it. Then they'll take the lid off, drain all the juice, take the lumber out, pour another batch in there, and put that same lumber right back in there again. So they're not going to spend any money on aging. By the way, do you agree that if you were to put wine into this cask and say, I'm going to let it age for 7 to 10 years, do you agree you're not going to get any money for 7 to 10 years? So now you're going to have to let that float the whole time before you ever see a dime. Furthermore, what if you let it age for 22 years? Now you're going a long time before you're going to get any return. Do you think that's going to drive up the cost of that wine? Mm-hmm. How about this? Let's say that you have the perfect recipe. You use French oak barrels, you're going to use them one time, then throw them away, and you're going to let the wine sit in there for 14 years. What if you decide you're only going to do this for 50 barrels? Do you agree you have less wine? What's that going to do to the cost of the bottle of wine? If you ever get a chance, just for the hell of it, go to Google some of the expensive bottles of wine. Some of them, $3,000 and $4,000 a bottle, $6,000, $7,000, $8,000 a bottle. If you ever find yourself in a situation where you have too much money, this is what you could do with it. This is the facility I have in my garage. That's me when I used to have a beard and I weighed 100 pounds more and had hair and wore glasses. So one of the things we need to understand is that wine and beer is made through the fermentation process, correct? Well, there's something else out there in the world, right? The good stuff, right? How do we make these? Look at all this. There's Jack Daniels, that's some good stuff. There's Southern Comfort. Here, where I travel all this way to drink Southern Comfort. Southern Comfort and Coke. There's some Jamesons. Here's some Absolute and some Kettle One. Now we're talking. How do we make this stuff? Any idea? Huh? We have to start with fermentation, except the problem is, do you think that this has more alcohol than beer and wine? Oh, yeah.
And we don't use grapes for it, right?
We're going to talk about what we use. Oh, the sulfites, by the way, are used to sterilize. Sometimes the sterilants contain sulfites, and the sterilants in between each batch. That's one source of the sulfites. Sulfites also come sometimes from chemicals that are used in the growing process, whether it's pesticides or herbicides. So how are we going to get this much alcohol into that little bottle? The distillation process. So we're going to use fermentation and distillation, distilled beverages, right? There are people that think the two are the same. They're not even close to the same. So what I'm going to do is I'm going to go ahead and call an expert witness.
Does it have to go through some kind of a little machine?
I'm going to show you how to make that machine. This is Carol. She gets drunk with economic speed.
Cheap date.
She is very cheap. We have to understand how much alcohol you'll find in beer and wine. I know you get numbers bigger than this. I'm talking about the average wine that you find on the shelves at the supermarket. Beer contain anywhere from 3 to 6% alcohol. Yeah, Arrogant Bastard is what, 8.9 or 9.1 or something? What is it? 8.2. Stella is what? 8 something? Anybody know?
Yeah, it's like this one.
So, but typically the stuff you get on the shelf, Miller Genuine Draft, Corona, Coors Light, or Budweiser, that stuff, 3 to 6%. Wine can be 7 to 15%. The maximum alcohol content is 17%. Can anybody tell me why? That's the maximum alcohol I can get when I try to ferment something. That's her Ebola alert. Tell me why this is the maximum number.
No more reactive sugar.
Oh, I'll pour more sugar in. I'll dump a whole bag of sugar in there to try to get this number higher, but it won't get any higher. You know why? And 17%, they're swimming around in their own alcohol. They're swimming around in their own excrement. They can't live in greater than 17% alcohol. Remember, the yeast are in there making alcohol. Now you get to 17%, they're dying. They're getting drunk and then they're dying. Right? So the idea here is this is the most you can get from the fermentation process. So we have to get to higher amounts. 40% is what you want if you want to go into a beverage that's going to go onto the shelf. These bottles like vodka, rum, gin, etc. And let's just have you remember too, 80 proof is 40% alcohol. So why don't you tell me what 50% alcohol is? What? No. If 40% alcohol is 80 proof, 50% alcohol is 100 proof. Let me go backwards. Bacardi 151. Tell me how much alcohol is in that bottle. 151 proof. It's not 151% alcohol. Nothing can ever be 151%. So Bacardi 151 is 151 proof, or 150 proof. Can anybody tell me how much alcohol is in that? 75% alcohol in Bacardi 151. Right? What's isopropyl? 70 or 90. Right? So that Bacardi 151 is some serious stuff, right?
You guys should light it on fire.
What?
You can put a fire on it, it'll light up.
Kate, is there anything that's better than 75%? What is it? You know it for a fact? Or are you just guessing? And what you've seen the number?
Yeah.
Because you drinking it and acting crazy is still not, I need to know the number.
No, there's actually one with 87%, and there's one that's abandoned in most countries, 97%.
Okay. Anything in the U.S.? Yes. What do we call it? We don't call it moonshine. Well, there's Everclear. Ever heard of Everclear? You guys have never heard of Everclear? I'm giving you an education. Everclear's in the 90s. Could be 95%. A lot of guys drink it. It's great. I had a story of a patient that he was turning 21, so they gave him Bacardi 151 and they lit it on fire. Happy birthday to you, happy birthday to you, happy birthday to you. He didn't drink it. He drank it, and now it goes, but it doesn't hurt because it's really going to burn off the alcohol, then the alcohol burns away, and because his skin isn't burning, it's the alcohol that's burning. So it really doesn't hurt. I mean, it singes the hair and stuff, but it doesn't burn. The problem is the people that gave him the drink reached across the table and put out the fire and broke his nose. So how are we going to get this 40%? Because everything dies at 17%, so we're trying to get to 40%, right? And if we're going to do this, let's not distill wine, grapes and barley. Instead, Tell me what comes from barley and rye. We distill barley and rye. Barley's beer, but barley and rye, we can also get two other things, and wheat. What else can we get? If we distill barley or rye or wheat, what kind of alcohol do you see on the shelf? Bourbon, whiskey. Okay, scotch. Next, corn. You'll typically get, what can you make from corn? I shouldn't skip corn. What can you make from potatoes? You can make shit. W. Juniper berries. What can you make from that? Who said that? See that in the back of the room? Gin. She's right. How about sugar cane? Okay, I'm going to give you a hint right now. Ready? Okay. See? I'm not going to wear that hat. Come and ask me.
You forgot the agave cactus.
What?
You forgot agave. The one that made them make
Oh, yeah, tequila. Oh. It's because I've puked on it so many times.
If you try the tequila in Mexico, it's different. It tastes different.
I know.
It tastes better.
I know. That's good because I usually end up tasting it twice. Okay, let's talk to you about how to get this 40% alcohol. Ready? We need to build one of these in class and laboratory today.
Yes.
Yeah! Yeah, I wouldn't get fired at all. Furnishing alcohol to a bunch of college co-eds. Okay, ready? We're going to take the solution here that's already been fermented. So this already has what percent? Already has 17% in it. Because you need to start with something that has some alcohol in it. Then we're going to put a little candle under here. And what's going to evaporate first? Water or alcohol? Alcohol evaporates first, doesn't it? Has a lower boiling point, right? Water has a higher boiling point than alcohol. So alcohol has a quicker boiling point and will evaporate, turn to vapor quick. So this vapor in the very beginning of the stage is all what? It's all alcohol. The idea is this vapor is going to fill this, and then it's going to fill this little tube. And right here in the tube, you need to cool the tube. You can wrap it with ice packs. You can wrap it with little coils with water going across it. You just need to cool the tube somehow. You can refrigerate it. And when you cool the tube, this vapor is going to turn back into liquid and run down the tube. Tell me what percent of alcohol we have going here. Nearly 100%. What's going to happen is you got to be careful because if you continue to leave the heat here too long and all the alcohol has been evaporated, now you're going to start evaporating what? Water. Then water's going to get in there. Ooh, plug that up so no water gets in there. So you're going to get, if you do it right, you can get to close to 100% alcohol in here. But then remember, we're going to take this and it's going to be mixed back into all of the other things that give, quite frankly, the qualities you're looking for when you have scotch or bourbon or gin or vodka. But I know that a lot of you aren't interested in those qualities. You want something that you can drink and you can't taste the alcohol. That's what you're interested in. This is the facility I have in my backyard. Therefore, let's talk about two questions on your exam. Maximum alcohol content of beer, maximum alcohol content of wine. And if your numbers aren't identical to those numbers because you got them from another textbook or somewhere else, I'm okay with that. Your numbers have to make sense. Agreed? So I'm going to be asking you the content of alcohol in beer, alcohol content in wine, and the maximum alcohol content in fermented beverages. Another question I'll be asking you is the relationship between alcohol percent and proof. So from now on, when you see 80 proof on the shelf, you know that's 40% alcohol. Agreed? Giving you guys an education. Next week, I'm going to teach you how to play craps and how to count cards in blackjack. 2-deck shoe maximum.
distillation process is not on the test, right?
No. Has to taste good. But I'm guiding your food preparation. This is like garlic bread, doesn't it? Takes gigantic loaves of garlic bread. It's cheese. So when we think about the cheeses, I want to just kind of a cheesy lecture. Ready? Soft, semi-soft, and hard cheeses. Soft cheeses are what? Cottage cheese and cream cheese. Either eukaryotes or prokaryotes are used to impart flavors in some of these cheeses. Soft cheeses, cottage cheese, and cream cheese. Semi-soft cheeses like Roquefort and blue cheese and gorgonzola. And hard cheeses and yogurt products. For all of these, they'll typically either use bacteria or mold, or sometimes a little bit of both in different stages to make cheese. Making cheese is much more sophisticated than making alcohol. That's why I don't make cheese. Also, too, with yogurt products sometimes contain lactobacillus, not strep, but lactobacillus and some unacidophilus. Why is it good that these yogurt products contain those two live, active cultures? I couldn't have said it better myself. Let's see. I don't care about this slide. But I do care about this slide. No, this one. I care about this one. So here you are putting the bacterium in here. You're also going to put their nutrients in here. You're going to put other chemicals in here. These impellers don't spin around quickly. They just go around slowly so that all the organisms can come in contact with all the nutrients, right? Then at some point, these organisms are going to be making something for you. And when these organisms make something for you, you're going to take that product, you're going to recover that product, and then you're going to have to filter it and extract it and purify it, and then now you have something that you can sell. There are two ways to do this. Another question on your exam. You guys remember this? There are two ways to do this. Batch fermentation and continuous feed. I'm going to go back to this one. Batch fermentation is when you do this, siphon off your product, throw all the dead organisms away, and start again. Do it again in another batch, take off your product, throw them away, clean everything out, do it again. Alcohol is typically made in batch fermentation. You don't save the yeast and save the grapes and make some more wine, throw everything away and bottle what you have left. There's what's called a continuous feed system, where you will keep organisms in the stationary phase for this long, long period of time. If you can keep organisms in this phase for a long period of time, you could make money off of the product during that entire phase. That's called a continuous feed strategy versus a batch fermentation. Everybody see the difference between the two? It's pretty easy. Whether it's antibacterials, enzymes, all types of drugs, you can get yeast or you can get bacterium to make these products for you, purify them, package them up, to get your money back. They do this in pesticides. There are even some enzymes that are used in detergents that will help eat and destroy compounds. She hates this picture because she doesn't like her hair in this picture. But she's standing with two cops. Cops don't carry guns in Ireland. Kind of interesting. I wouldn't be a cop in Ireland. Because I want a chance to shoot somebody. It's in the brochure. I found this on my camera. I'm telling the truth. I do not know any of these people in Central Bureau. I don't know who they are. I don't know who they are. I don't know where. This is in the Temple Bar District in Dublin.
Girls look very Irish for sure.
Now I'll say this. This could be the reason why I don't remember. So the study guide's up for exam number 2. We've just finished. There's not going to be any questions regarding what my blood alcohol was or whether I was able to pass a field sobriety test. You could throw a rock in the Temple Bar District and you could hit like 9 bars. It's amazing. And they're all very, very friendly, nice people. People get drunk over there, they don't, well, never mind. I should probably leave that alone. Any questions on chapter 2? So exam number 2 is going to be 9, 10, 11, 12, 13, 14, is that right? Oh. 10, 11, 12, 13, 27. 9, 10, 11, 12, 13, 27. At 27, I'm only going to ask you 2 things. Alcohol content and continuous feed versus batch on the table. So we're going to start 14. This is important. I should be finishing 15 today, right?
No.
Oh, I am? So I can get caught up. So you guys ready? This next lecture right now goes for exam number 3, and all the PowerPoints are available to you, right? There's a study guide available to you. That's great. I'm going to put 3 up sooner rather than later, like as in the next week. Okay? Because it is a very difficult exam. So as soon as I remember to do it, I'll put it up. Anybody in this class ever taken an immunology course before? This is what makes it hard, because now I'm going to teach you some things that you've never learned before. For instance, the alcohol lecture, all of you knew that. Okay, you ready? So what I'm going to teach you, all of the components and in what order they work in order for your immune system to work. And in order to do that, I also have to teach you what vaccination is all about, and how vaccination and your immune system helps protect you from diseases. And then I have to teach you what happens when the immune system isn't working properly. Number 1, let's say the immune system isn't working at all. What's going to happen to you? Yes. Yeah. If the immune system is working overtime and is working at inappropriate levels, does anybody know what the signs and symptoms there might be? Could, if it's anaphylaxis, allergic reaction, allergic response, anaphylaxis, rheumatoid arthritis. Your immune system doesn't attack its own immune system. The immune system attacks your own tissues. Joints, kidneys, liver.
Like lupus?
Lupus. So I'm going to teach you all about the immune system. So I'm telling you right out front, exam number 3 is the most difficult of the 4 exams you get in my class. All right. I'm going to teach you the first line of defense, the second line, and the third line of defense. The third line of defense is the hardest, highly, highly specific, whereas some of these things aren't so specific. So if I start, I'll go with the first line of defense in just a minute. I want to see what I have here. I'll do the first line of defense from this page right here. barriers. You agree that your skin is your first line of defense from infection. If there's a break in the skin, that makes sense, but that's where the organisms get into the skin, right? So those are the physical barriers. There are chemical barriers. Can you think of any chemicals that you secrete and where you secrete them that, believe it or not, helps at least flush or wash away or somewhat destroy bacteria and viruses? Can you think of any secretions?
Tears in the eyes.
Okay, so you've got lacrimal oils that are always going through the eye and down the nasolacrimal ducts. You've got tears that are being secreted. And then you've got the mucous membranes, which is secreting mucus, agreed? And then when you sneeze, when you get rid of that mucus, then some of the organisms go with it, right? Anything else? Sweat, believe it or not, helps flush out and flush away bacterium. And of course, it's the salinity content of sweat that sometimes makes it difficult for some organisms to survive there.
Earwax.
Earwax forms a barrier between the tissue inside the ear canal, the external ear canal. So wax basically helps protect it. The wax in itself doesn't really have any antibacterial properties. And if I say that sweat, tears, has antibacterial properties, you have to understand they're very, very weak antibacterial properties. I'll talk about genetic barriers in a few seconds. So this is our first line of defense. Our second line of defense is very simple. It's everything that's under the skin. So if an organism does indeed penetrate the skin through a cut or an ulceration or a laceration, now we're going to have an inflammatory response, interferons, phagocytosis, and complement. I'm not going to put on my exam. It's too sophisticated and it takes too long. So our second line of defense is what happens if the organism actually makes it to the bloodstream or makes it to the tissues or actually gets absorbed into the intestine. So right now is a good time for me to discuss the definition of what's inside the body and what's outside the body. You do understand that when you eat food that's got bacterium on it, so it goes to the stomach, by the way, can you think of any chemicals there? That might, okay. Let's say that you eat something that's got a lot of bacterium on it. It goes down the esophagus into the stomach, you're feeling a little nauseous, but now it leaves the stomach, it goes into the small intestine, right? What's the small and large intestine going to do if there's a lot of bacterium on the food that you just ate? You bet. They're going to shut all the doors and say, we're not absorbing anything, and we need for you to increase peristalsis. And that's when you're going to just barely make it to the bathroom. And then what's going to happen is everything's going to leave. And people will ask me, can I get something that's going to stop that peristalsis? And the deal is, if you're traveling and you have traveler's diarrhea, it might be a good idea, because I don't want you to stay in your hotel room for 2 days until this thing, finishes. So I might give you something to slow down the peristalsis, but the best thing is for that peristaltic activity to continue, and for you to drink plenty of water, and then you can get rid of that organism, agreed? Mm-hmm. Do you agree that the organism that went into the intestines, and then right out the other end quickly, never made it into the body? You know that, don't you? You know that the mucous membrane that you see in your mouth is continuous with the esophagus, the inside of the stomach, the inside of the small intestine, the inside of the large intestine, all the way to the anus. It's all continuous. So that food can pass through there, but it only makes it into the body if it gets absorbed by the intestine, correct? Tell me where most of your water is absorbed.
Colon.
Large intestine, colon. Okay? That's why you get some patients that will take a bottle of vodka, right? Google it, you'll see. The absorption's amazing. That's why we give some medications through suppositories, right? Phenergan suppositories. Anybody ever heard of a Phenergan suppository? It's a medicine that keeps you from throwing up. People say, oh, can you give me these pills to keep you from throwing up? No, because what's going to happen? You're going to throw them up. So here's suppositories. It's called a Phenergan suppository. I write you a prescription. Here's one for now. They come back, they say the suppositories don't work. Well, did you use them correctly? Well, what did you want me to do? Shove them up? Yes, because of the absorption in the colon, right? You can absorb water, you can absorb all your liquid in the colon. So do you understand why, if you have diarrhea, what's the big problem with that patient that we're worried about? Dehydration. Okay, so even though we've got food that's in the intestine and still hasn't made it into the body. When I talk about making it into the body, I'm talking about getting into the bloodstream and getting into the tissues. This is a good time to review the places where we don't want to see any organisms growing in the body of the, can you tell me those places? Bloodstream. Where else? We don't want to see any organisms. Urine. It's supposed to be sterile. So the meninges, right? The cerebral spinal fluid. 3 shining places we shouldn't see any organisms. Can you think of any other places we shouldn't see organisms? We're going to see organisms in the respiratory tract.
Spinal, cerebral area.
We already said that, cerebral spinal fluid. The orbit of the eye. So in the eye, inside the globe, you have an anterior and posterior chamber. We never, ever have organisms growing inside the eyeball. Ever, ever, ever. Okay? And lastly, the tissues that surround all the connected tissues. All the intercellular spaces. The space between the cells and in the tissues, we don't want to see organisms growing there. Right? Another physical barrier is nasal hair that traps the largest particles. I've seen some people that are capable of trapping a lot of particles. All right. Chemical barriers, sebaceous secretions, right? Another perfect example, sweat, skin's acidic pH, hydrochloric acid, digestive juices. Okay, the fact that this textbook says that semen contains antimicrobial chemicals, just leave that alone. And the vagina has a slightly acidic pH. Now, I want to show you this genetic barrier for just a second. This is an example of a balanced polymorphism. You guys know what sickle cell anemia is. What is it?
It's where the cell is a holy shape and it can't carry enough oxygen to carry through the body.
So here's the cell that's typically round, and then when it collapses and folds inappropriately, now it can't carry oxygen. So do you agree that it's a genetic trait? Do you agree that you could be heterozygous or homozygous for sickle cell anemia? Meaning you get one from mom and one from dad, or just one from one parent and the other one is the wild type. So you could either be homozygous or heterozygous for sickle cell anemia, correct? If you're homozygous for sickle cell anemia, do you agree that there's a chance that you could die of sickle cell anemia? Right? If you're heterozygous, there's less of a chance, right? Okay, now let's switch gears and talk about a eukaryotic organism that invades red blood cells. Do you guys remember that organism? Eukaryotic organism that's carried by mosquitoes, found in Africa, that invades red blood cells. Malaria. So malaria